So here I am hopping back onto my live stream. This is my new habit, my New Year's resolution, if you will, to live stream some of the open source work that I do, typically in the mornings here on Swiss time. So the topic for today is a little bit of RaptorJIT performance work. RaptorJIT is a fork of LuaJIT that I'm developing because, as you may have heard, LuaJIT, its maintainer Mike Paul is not doing new feature development anymore. So somebody needs to move the project forward, and I'm going to do that under the brand of RaptorJIT, which is taking shape nicely. But so I'm kind of gearing up for the first 1.0 release of RaptorJIT now, and before I've done that, I've been a little bit careless or loose with performance testing. So I often merge changes onto the main development branch without thoroughly checking them for regressions, even though I actually have a pretty decent performance regression test suite. So in the last episode, we brushed the dust off that performance test suite and got it running again. And what we're going to do today is first we're going to look at the results. We're going to look at the results that came from running that test suite yesterday. I've had a quick sneaky peek, so I know that there is a performance regression, so we're going to have a little bit of a poke around and see what that's all about. Then I want to set up a proper master and development branch pair on GitHub with the idea that I can kind of casually push code to the development branch, and then a continuous integration will benchmark that thoroughly, and before it gets merged onto the master branch, it will get a clean bill of health. We'll know that there's no performance problem, so that the master branch will always be good. This is the way that we do things on Snap. We typically have a month or so window that we do a lot of hacking on the development branch, and then when everything looks good and all of the benchmarks pass, we merge it onto the master to make a release. And finally, what I would like to do as a stretch goal is to look at automating the interpretation of the benchmarks. So the benchmark suite produces a pretty detailed graphical report, and I don't want to read that every time. I want to kind of have a sanity check to tell me if there's something there or not, without having to figure that out myself. So let's get into it. And I'm working from my home office here. I have a dog sleeping at my feet. I have kids running around the next room, so there'll be a bit of background noise, but you'll get used to it. I have. In we go. Okay, so yesterday on the stream, we fixed the RaptorJIT performance benchmark script, which is written in Nix. And then what I've done is I have run a set of benchmarks. So I don't know, there's about 20 benchmarks that are borrowed from the LuaJIT benchmark repository. I ran each one for 2 different versions of RaptorJIT because I want to check if I've done anything, if I've broken anything recently. So I tested the current master branch of RaptorJIT against an older version, which was the last one that I ran the benchmarks on. So the idea is that we'll see if anything, there are any interesting differences in the intervening commits. And for each benchmark, I ran it 100 times. And the reason for that is that I want to not just get a number. You know, a number is not a good summary of a benchmark, especially when you're dealing with complex systems. So there can be some jitter if a benchmark, if it falls out of JIT code and runs in the interpreter, then it's probably going to be doing some garbage collecting, which can have a little bit of an unpredictable impact on performance. And some of the benchmarks even written specifically to try and provoke the JIT into doing something non-deterministic. So the way that I always run the tests is to run them a lot of times. So in this case, 100 runs of each test, so that I can see the shape of the distribution of results, not just to get a number or an average, because there's a risk that this misses something interesting. So anyway, 2 versions of RaptorJIT, the latest one, which may have problems, and an older one, which is a reference, and about 20 benchmarks and 100 runs of each benchmark for each one. Let's see what was produced. So here in the shell, this is just the output of Nix having gone off and done a parallel execution of all the benchmarks. And what it kicks out down here is it produces a CSV file. I can briefly summarize. That just gives a list of each individual result, which version it was from, what the benchmark was called, how many instructions it ran, how many cycles it elapsed, and then it also kicks out a couple of PNG files, which is from running an R script over over this. So the PNG files look like this. There's two of them. This is the first one. So it's big, and a pitfall that I often fall into when looking at graphs is to just go blah 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 blah, without kind of giving enough context to have any idea what's going on. So I'll try to go a little bit more slowly. So this I can scroll around a little bit. So this is a little bit bigger than what you see on the screen at any one time, and it's split into a bunch of panels in a two-dimensional grid. Each panel represents one of the benchmarks. This is a benchmark called Array 3D. This is a benchmark called Binary Trees, and so on. And within this panel, there are results for two different software versions. The latest one, which is the RaptorJIT master branch, and the older one, which is the one I want to use for reference. I want to compare with. And the latest one is always in red, the older one is always in blue. So on the kind of the x-axis, this is just random jitter, so that each point here represents a single benchmark result. So there's 100 red dots there because I ran the benchmark 100 times, and there are 100 blue dots there. And there's a little bit of alpha transparency, and they're kind of open circles, unfilled circles, just so you get a little bit of a visual idea of how they cluster. The idea is to be intuitive. And on the y-axis, 100% here is the average performance of the first software version, which is the red one. So if a point is on that 100% line, it means that it was exactly the same speed as the average speed of the first software version. If it's above, it means it was faster than the average, and if it's below, it means it was slower. So the red ones here are being compared with their own average. So this 100% is the average performance, which is the number of cycles that elapsed while running the benchmark. And these ones down here are ones that ran slower than their own average, and any a little bit above would be faster than the average. So this up and down gives us an idea of how much jitter there is. So we can see on the Array 3D, for example, that the worst case, there was one of the results ran at only 60% of the average. So there's obviously something a little bit funny there. And then when we look at the blue one, it is also being compared with the average from the red ones, because we want to be able to do a side-by-side comparison here. So this blue one down there is, about 20% slower than the average red speed. Anyway, anything sitting on 100 is fine, above 100 is good, and below 100 is bad. This is the basic thing. And generally what we care about is whether one is doing better than the other. So let's just browse along. So in the first one, the Array 3D, it kind of looks like they're pretty similar. There is a little bit more, there are a few more kind of low outliers on the red side, and it's not really immediately obvious whether that's not obvious to me anyway immediately, whether that's due to some systematic problem or just a kind of a sampling thing. We ran 100 tests. A couple of them were slower on that side. It might be that if we ran 1,000 tests, they would look more similar, or if we reran it. So that's something that would be interesting to look into, but I don't see any kind of a smoking gun there right now. Similar-ish kind of a story over here, actually. It actually looks like there's a kind of, looks to me like the red one is doing a bit better in general. And they both have a little problem with some runs being a little slow. I'm really interested in this, actually. I would like the benchmarks to look like this, what we see on the third one here, where everything clusters very tightly. So every time you run the benchmark, you get the same result. So my goal in performance testing is to try and design the benchmarks to make it as hard as possible for the JIT to make things consistent. In a kind of adversarial way. The benchmarks are supposed to make things hard, they're supposed to expose problems, and then to try and work on the JIT to get that under control. So the benchmark, when I work on the benchmarks, I'm trying to spread things out, and then when I come around and work on the JIT, I'm trying to compress things down. That's my kind of two hats way of working on things. Anyway, this one looks, it ran very consistently on both branches. It does look like the older version was ever so slightly quicker than the new one, which could be interesting. Here they look about the same. On the Euler benchmark, the older version was distinctly slower. So actually, this new that's not a regression. That's an improvement on that particular benchmark. The latest version is outperforming the previous one. This one is identical, and this one is identical. And life. Okay, so life. This is one that jumps out a bit more, right? This is a very, very clear-cut performance regression. So what we're seeing here is that the performance of the old version, the performance of this benchmark with the old version of RaptorJIT has 160% of the performance of the current master branch. So if you downgrade to an older version of RaptorJIT, your performance goes up by 60%. So something's wrong there, and that looks like a great candidate for something that we could look into because it's such a strong pattern. And the nice thing about this is, sometimes it's very difficult to reproduce a performance problem. Like over here on this first panel, we might have to really know whether the performance of the array 3D between the branches is the same. We might actually have to run that maybe 1,000 times to actually be able to say with statistical confidence whether there's any difference or whether they both have a certain element of randomness and we're getting tricked by that. But on the life benchmark, it's totally different. So each one ran 100 times, and the latest branch never outperformed the older branch even once. So it should be very, very binary kind of a thing that we should be able to see that the old version gets performance, X, and the latest branch gets performance 60% less than X, which is great. And just skimming around to just verify that that is the most interesting one. I would say that is the most interesting one, yes. And one thing I just want to highlight as we go past, on the roulette benchmark, so the performance of both branches seems to be the same, but this is a benchmark that's specifically designed to provoke non-determinism from the just-in-time compiler. So most of the time it will perform well, and sometimes it will perform poorly, and that's why you see these two clusters. It's a bimodal performance distribution. Most often it performs quite well, but also quite frequently it performs more poorly. So that benchmark was written specifically to expose a bad case in the compiler, and I'm very interested in improving the compiler to eliminate this bottom hump down there, so that the performance is always good. But I digress. So okay, definitely the most easy to investigate and most pronounced difference is on this life benchmark. So what we're going to do, we're going to look at our to-do list again, and we're going to say that we have checked the benchmark results now, and now we want to investigate a regression, which is going to be this life one. And I mean, there's a lot of different ways that we can look into what the issue is. So on the one hand, I've written a bunch of these fancy development tools. You might remember this from previous streams, where we can run a script and we can get a lot of detailed profiler information, and we can drill down and we can see the generated code and all of this kind of thing. So we got a lot of tooling there, but that's not what I'm going to use today, and that's for two reasons. The first reason is that this tooling is really new, so it only exists in the latest version of RaptorJIT. So in the older version, the virtual machine didn't contain any of the necessary instrumentation to produce the data that goes into this tool. So I would need to backport all of that if I wanted to analyze, to visualize how the old version of the compiler is behaving. I don't want to do that. But more to the point, this is just such a perfect use case for Git bisect. Absolutely what Git bisect is ideal for. So we have two versions of the software. One of them has this performance, the other has this performance, and there's been some number of commits made to the Git repository, and we just need to look for when did the performance change, which change was it that made us go from performance A to performance B. So let's just do that. So first, let's see how many changes there were in here. So I actually currently have a little temporary directory here with both versions checked out separately. So if I go into the old version here and I say, what version was that? Okay, so the one that I picked as the old version is this commit here, which was when I merged the this slow LEA performance optimization a ways back. So this is just an older version of RaptorJIT that I happen to have run the benchmarks on previously. So now the question is, what else has happened between that commit and the current master branch? So we hop over into this checkout and we say git log, and maybe to start with we'll just get one-line summaries, and we'll just look at the merges for now. Merges, I always use merge commits to pull things in on pull requests. So the merges will basically just show every time I've clicked the merge button on GitHub. In this case, it's the high level. It's when some collection of commits lands on the master branch, and we look from this up to RaptorJIT master. And I've done something wrong. Unknown revision. Okay. So why was that not a known revision? No, it is known. I obviously typed something wrong. Is it? I used, yes, I used the wrong name of the remote. Origin master. Okay, so these are the merge commits that have been made. So it's actually been a reasonable amount of activity of stuff going into RaptorJIT in that time. And let's see a little bit more detail how many actual commits. So instead of looking at merges, we'll just graph all of the commits. So this is all of the commits that have come in, and any one of these, in principle, could be the reason that performance regressed. And that's the cool thing about git bisect, which I'm sure you already know about. The whole point of git bisect is that you can very efficiently search for the commit that caused something to happen, because you do a binary search. So you have this many commits that you need to check, but each time you run a test, you divide by half. So it only takes a logarithmic number of steps to find out which commit is the interesting one. So here the total number of commits, well, there are 178 commits, so it's going to be like 8 tests roughly going to be needed in order to isolate the right one. So it's not many. 8 tests is not that many actually. So we can probably just do this step by step interactively, where we check out one version and we manually run the life benchmark and see, is it the high performance or is it the low performance, and then go one way or the other based on that. If it was thousands of commits or tens of thousands of commits, then it would be worth writing a script. Or if the test took a really long time to run, then it would be worth writing a script that automatically evaluates whether the performance is good or not. So we'd run the life benchmark and we'd pipe that into an awk script or something that would then tell Git whether that was good or bad, so that the whole search could go automatically, and we could go off and walk the dog or something and come back and see the result. But the test is probably only going to take a few seconds to run, and we only have to run it about 8 times, so it's not worth bothering with. So let's just run it the first time to see how that is done. So we'll build RaptorJIT. It doesn't take terribly long. And then we will go into the test suite benchmark directory, and it's the life benchmark. So we might have to give it some parameters. So there is this file that says how the continuous integration should run each benchmark. So if we look for the life one, it doesn't take any arguments. So let's just run that. And we'll run life. Okay, there it goes, running away. So what we're running now is the latest version of RaptorJIT, which is the one that we think is slow. So this took 8.6 billion CPU cycles to run. So that's our slow long time, is 8.6 billion. And if we run this again, we're expecting to see basically 8.6 billion again, more or less, because if we think back here on the life benchmark, okay, so it was all within about 10%, say. So we expect every time we run it, the difference won't be more than about 10% from the average. So we shouldn't have to keep on running this again and again. So we got 8.6, 8.68, and just for example's sake, we do it one more time, and we're expecting to get something close to 8.6 again. Yeah, 8.62. So this is why this is some value in taking the statistics, I think. So when I see that this is 8.6, I'm actually confident that this is not that the performance is actually wildly randomized and variable. I think that this is representative of the actual performance of that branch. So if we run a version of RaptorJIT and we see it take about 8.6 billion CPU cycles to run that benchmark, we're going to say that's one of the slow ones. And then if we find our point of comparison, where that was the commit that we denominated as the good one. So let's just manually test that one as well to see. So 8.6 is our, we'll write this down while we're at it. 8.6 billion cycles is bad. How many cycles is good? I mean, we know it's going to be about 60% reduction, but let's run it anyway so that we don't trick ourselves in some way. There is the commit. Let's grab that one. Build that. And then let's run the benchmark again. Oops, and we'll run that in perf start. Took 1.5 billion cycles. Which is actually quicker than I was expecting. Okay, so that doesn't quite make sense to me. I was imagining it would be more like 3 or so. I cannot immediately account for why why the performance difference is so big. I thought based on this it was going to be smaller, but anyway, I guess for the purposes of tracking down which commit is responsible, we can take that later. At the moment, we'll just see. We'll try to find an inflection point when it went from being fast to being slow, and then we can later double check whether there's anything kind of fishy going on with the benchmarking. It's nice to be able to check things from a few different angles. It's nice to have statistics, it's nice to have visualizations, it's nice to have some happy tests, and to be conscious if things line up or not. So we're going to write down here 1.5 billion cycles is good but too good. So that's something that we're going to want to look at. Anyway, now it's kind of over to Git. We're just going to be a pair of helping hands for Git now. We are going to say, remind ourselves what the arguments are to git bisect start. So we're going to say git bisect start, and first give the bad commit, which is our latest one, and then we're going to give a good commit, which is the old one that we're on now. And then we're going to ask. Yeah, we're gonna step through. You probably know how git bisect works, but we'll see anyway. Well, just give me 5 seconds. So git bisect start, and first it wanted memory like a sieve. First it wanted the bad commit, and then it wants the good commit. So we use the commits that we had in our log. Git bisect start. The bad commit is origin master, and the good commit is 742104F8 blah blah blah. Okay, it tells us we have it's picked a commit now in the middle it wants us to test, and after this there are going to be 71 more candidates to test, which we're going to binary search through in 7 more steps after this. So the way that we're going to test it is to always do the same thing. We're going to say make clean, make -j, and source/RaptorJIT test suite benchmarks life. Of course, we need to run that with the perf stats. So this is going to tell us, it's going to build a clean RaptorJIT. It's going to tell us, oops, okay, so that one didn't build. And that's always a risk, right? So when you're bisecting through a bunch of commits, and I'm usually pretty liberal about pulling in commits. So when something lands on master, it's important that the sum total commits are okay, that the merge commit that comes in is good, but I'm quite flexible at having some broken commits down near the edges of the graph. So for me, this doesn't really bother me. I just need to remember what is the git command to say that this version, this commit was not testable, so that it can pick a new testable one instead. So we're going to skip this revision. So it didn't build, so we can't test it, so we can't say whether this comes before or after the problem was introduced. So git bisect skip. Fine. And now we're gonna, so now Git has picked us a new revision, and we're just going to run the test again. And we're just going to keep doing that. Anytime we get a revision that is broken, that crashes, or doesn't build or whatever, then we just skip that. Okay, workload failed, no such file or directory. This is probably also a non-working. I didn't goof the path. This is also a apparently a non-working build, which again I think is fine. I don't. Some repositories kind of have a policy that every single commit should build and run and test, so that you can bisect them all. But for me, I'd rather just be very forgiving at the edges of the commit graph and just skip these things and bisect. So we just skip again. That's no problem. This time it's running. And now, okay, but that's interesting. So now it took 5.5 billion cycles, which is actually kind of more like what we expected, or what I expected the good result to be. So we've said that 8.6 is bad and that 1.5 is good, but what about 5.5? I'm going to say that that's good as well. Because this is based on the statistics we saw in the R graph, this is the good performance that I was expecting. I still think that this other good performance is anomalously good. So I'm going to tell git bisect that this is one of the good commits that came before the problem was introduced. So I say git bisect good, and git says great. Now I can do the next step of the binary search, discard all the commits that came before. And in 5 more steps, we should get where we want to go. So now it wants us to be helping hands and test another version, which we do in exactly the same way. This version compiled and is running. This took 8.6 billion cycles. So this is slow. This one. This commit is one of the bad ones. So we will tell that to Git. We'll say git bisect. This was a bad commit. And then Git says, okay, that's great. Now I can forget all the commits that came after this point because I know the problem was somewhere before. So we have 4 more steps to go. And Git has automatically checked us out the next version to test. We test that now in exactly the same way. And I guess it's fortunate that it's only 7 or 8 steps that we're testing here, right? Because this would get old. I hope I'm at least not exhausting my own patience yet at this point. 6.5. I'm going to call that. I want to run this a couple more times actually, because I think that sounds like a good result, but I'm not so confident yet. So I want to run it a few times. 6.6. Okay, so it's this version is pretty consistently taking about 6.6 billion cycles. So it's interesting. So in the original benchmark, I own, you know what, I think it's worth recording which commit we're on, because I would actually like to rerun the full big benchmark sometime. Instead of testing 2 different versions, I'd like to test maybe 5 different versions, including this one, so that we can actually see how the performance has evolved, because we only compared with 2 points. But clearly there was more than one change that impacted the performance of this benchmark. And I find that really interesting, actually, and I don't know what the reason is. And obviously this is a kind of an unusual benchmark in that it's doing terminal output and that kind of thing, so it's possible that the performance would be impacted by something, you know, like whether there's a stream flush in the runtime system or anything like that. So anyway, this is kind of surprisingly interesting. So I'm going to write down which commit I'm on now, which is this one. And I'm going to say that this is a good commit in the sense that the performance has not dropped to the low point that we're seeing at the end, the 8.4 billion cycles. So this is good-ish. And then we're going to continue onwards. So we're going to consider this a good one. So we're still looking for the point at which performance became roughly 8.4 billion cycles to run the benchmark. So git bisect, and we tell it this one was good. Now there are 3 steps left, so let us test this next one. Actually, I hadn't considered, but if this had run fully automated, there would have been a bit of potential to miss something interesting. So if next time I automate things, I'm actually going to do quite a bit of logging, so that I wouldn't miss details like this. Okay, 8.6 billion cycles. This is a bad one. Git bisect bad. This is the low performance. 2 more steps. This is good, good-ish. 6.6. So we're going to tell Git that this bisect was a good one. And now, actually, we should get our final answer, if I understood correctly. Very interesting. So Git is saying that performance dropped on this specific, when this specific commit was introduced. Or is that right? Hang on. Is this the last good one or the last bad one? Hang on. Let's test it to see. Because I'm just reacting because that commit, it doesn't superficially look like something that would have a performance impact. But it can be unpredictable, of course, with computers being as they are. Okay, no. So this one is, this seems to be the last good commit. So it's the commit after this that was problematic then, I suppose. I'm going to take note of this, just so that I don't do anything that screws up. Screws up the bisect state. I have to start over. That would be unfortunate. Okay. All right, there was 1 step left. So Git tells us now, hooray, it must be this commit that is the issue. So what was that commit? Log. This is, okay, sorry, the log is just confusing it. Let's isolate it. Yeah, so it was a merge commit that introduced that change. This is really interesting. So if you look at the diff, see the code. Heavens. I'm going to go back into Emacs where So what did this introduce? Pardon me, I have some demo effect going on here where I lose track of how I normally read diffs. Give me the diff, please, git show. Thought it was log minus p. I guess this is where the live stream is. If anybody is screaming out in their living room the name of the git flag I'm looking for. Tell me. Okay, it was okay, but there was a merge. It was a merge commit, so maybe that's the reason they didn't show me that. So let's compare it with the previous one. That's more like it. Fascinating. So in principle, this code is what caused it to run slowly. This is something I added to the kind of runtime system. Hold on. It's super fascinating. Let's just, okay, so before we dig into what this code is, let's just actually check for ourselves that this is truly where the problem comes from. No, I'm not convinced yet. So again, Git is telling us that that is the bad commit. I want to see that compared with its first parent, which is that change. So I'm going to now check out this allegedly bad commit. So the only thing here is I'm looking at the code and I'm thinking, wow, it will be very surprising and interesting if that causes a performance regression. I can't immediately account for why that would happen. So I wanted, before I dig into that, I want to just check, quadruple check that that is really where the problem is coming in. So now we've built this one again that is supposed to be bad, and we're going to run the benchmark again. And we're expecting to see the 8.4 billion cycle, 8.6 billion cycle bad result here. Aha. But another thing I noticed, which is quite funny, is that we got 10,000 generations on the test. It's possible that we're running, on some of the other ones, we're running a different number of generations. That's something else we should check for those early ones. Okay, but this was legitimately had the lower performance. So now if we check out previous revision, now we're expecting to see better performance. Yeah, 6.6, which was the one that we considered somewhat good. Okay, so I find this actually kind of fascinating. So oops, pardon me, I pulled the diff. So it really seems like this specific change has made the performance of that specific benchmark go down. So what this change does is track a little bit of extra state when the JIT generates code. So one of the things that I want to be able to do in RaptorJIT that's not supported in LuaJIT, as I can tell, is when you have, if we pop up the tooling again, this is a rendering of the intermediate representation, the kind of the high-level virtual, high-level, nearly machine code that the JIT is generating for a given piece of source code. So the next step after coming up with this intermediate representation is to assemble this, and basically each one of these boxes is an intermediate representation instruction, and each one of those is going to compile into some number of machine instructions. And this happens, this assembling happens in a linear way. So there's actually a mapping where you can say for each machine instruction which intermediate representation instruction did it come from. And I'm interested, I want to extend the UI here so that if I would click on this, you could see the specific assembler instructions for that specific IR node, so then you can get a feel for things. You can say, okay, so what is an add for an integer argument compiled into, and you click that, you would see a single x86 add instruction in that case, and you can do this on other interesting things. Constant hash table reference, you would click on that and you would see the assembler code specifically for locating a constant slot in a hash table. So that would be a cool feature, I think. And so I kind of proactively came into the JIT runtime system here, and I added a little array in each machine code trace that just keeps track of which IR instruction each machine code instruction corresponds with. So basically, when I assemble an IR instruction into machine code, I just have a little counter that says how many bytes of machine code are generated. This is to be able to create that mapping, so that then the tooling will be able to uniquely identify for each machine instruction which IR instruction it belongs to. So this is debug information that I added. So it's a really small amount of code here, right? I mean, obviously there's some more data. So when we allocate a trace, which is the structure that contains all the compiled code, we allocate a little bit of extra memory, which is one counter for each IR instruction. We zero that, and then when we are assembling, we just put a delta there. We say after we assemble each IR instruction, we just count how many bytes of machine code we generated. It's fascinating to me actually that this is causing a regression on the benchmark. I kind of, on the one hand, I'm guessing that there's something completely surprising reason, probably, that I've done something really silly now. It's not obvious to me. It's possibly obvious to you. It will probably be obvious to me later. Otherwise it can be actually very hard to imagine, but it can be because of the layout of the memory. That this extra allocation is somehow changing the memory layout in an interesting way. It certainly doesn't really seem like it can have the actual overhead of the recording can have any effect. So that's pretty cool. I need to look very carefully at what's going on here, but I'm not really in the mood to do that right now. But I'm going to take this as a known bug, and I'm going to come back to it with great interest another time. So let's write down our conclusion, which was that we had two conclusions. One is that introduced a performance version. Life benchmark went from 6.6 gigacycles to 6.5, something like. Anyway, that's quite fun actually. So if we just recap briefly what we did, we got a report from the benchmark suite that ran each test a whole bunch of times, and it gave us a summary of how each branch performed, how steady that was. We found a very striking difference here that we decided to look into. We then and it had this specific characteristic that the fast branch was never slower than the slow branch, which makes it a really nice candidate for a simple git bisect. You should only have to run one test each time. We then did the bisect manually, and we found a wider distribution of values than I was kind of expecting, which I guess is not, on the one hand, it's not strange. This benchmark only tested 2 different revisions, whereas when we do our manual testing, we tested 8 different revisions. So it's not unreasonable that we would see 8 different performances, you know, if there have been multiple changes that have impacted that benchmark. On the other hand, it seemed like the very first version we tested, which should have been this specific one here, had a much bigger impact, a much bigger difference. So it's kind of interesting. It's entirely possible actually that this benchmark is just being run in the wrong way. It might be a bit quirky. It might be that what we're really benchmarking is the terminal or line buffering or something. I don't know. That's a whole other aspect, is to actually look at the code for the benchmark. But it has been pretty cool. The Git has been able to go through and point us at a really a commit that is very relevant for some reason, which I would never in a million years have pointed my finger at if I was just reading the commit log. So we have a great future to-do item to look into what's going on with that one. But I'm going to leave that problem at that for now. So I'm going to take a short break, and then we're going to come back in 5 minutes and look at setting up a proper master and development branch for RaptorJIT, so that we can kind of be pretty liberal about merging code onto the development branch, but we can be very disciplined about only bringing stuff onto master when it passes all of the performance regression tests, so that master is always known good. It's good hygiene. That's the way that we do things in Snab and other projects. So it's about time to do that with RaptorJIT as we approach a 1.0 release. So back in 5 minutes. Also, that was nearly 5 minutes anyway. Now, after a good morning of benchmark report reading and Git bisecting, we're going to do something for the future. We're going to put our house in order on the RaptorJIT open source project, and we're going to make a new development branch which will be called Next, which is going to contain all kinds of weird and wonderful commits that may or may not be an improvement over the master branch. And then we're going to set up a continuous integration benchmark that tells us whether the performance is better or worse or complicated compared with the master branch and the next branch. The point of this is that we can develop in a fluid way. We have an integration branch where we can put things, but everything on master will be considered a release. So pushing to master will be a release every time, and we will always check the CI to make sure that everything is looking nice before we push to master. So from a user perspective, you can always pull from the master branch and you will always get the latest release, and you can be confident that it will have been tested for regressions and that kind of thing. If you want to use the latest, greatest scary code, then you would pull from the next branch instead, and you might prefer to use that for development, that kind of thing. So, I mean, we have 2 steps to do. We need to create the branch. We just have a master branch at the moment, and we need to set up a continuous integration job. So creating the branch is the easy bit. Let's just do that. We will say that the next branch for development starts off initially at the same point as the master branch is now. So let's just make sure we're up to date. And we will git check out and create a branch called next, and the starting point will be the master branch from the origin. And we will just double check we have the right commit there. We are on commit 02D59. Which is the latest one there. So now in my local repo, I now have a branch called next, which is currently identical to the master branch, and I'm going to push that to the origin repository. And now, see how quickly GitHub updates. We'll do a refresh. Okay, so now we have the master branch and the next branch, which is nice. But actually, okay, so we have the master branch and we have the next branch. At the moment, they're identical. The next time I do some new development that's ready for testing but not for release, I'm going to merge it onto the next branch, and only after it's known good will I let it come onto master. Then we actually have two CIs really. RaptorJIT already has a CI, which is Travis CI, which runs and tests every pull request. The thing about Travis is that it's only doing functional tests, so it runs the test suite at multiple optimization levels and this kind of thing. But all it does is give a functional pass or fail. It tells us if something fails to build or something crashes or something produces the wrong result. It doesn't do any performance testing. And they're running on some kind of unknown cloud provider environment, so I wouldn't really feel... I haven't tried, to be honest, but I don't think that these kind of environments are suitable for benchmarking. Again, if you look at our benchmark results over here, we want to see how steady the results are, how widely distributed they are, and to a certain extent, this is going to depend on environmental factors. It might depend on the temperature of the CPU. If there's any I/O involved in any of the benchmarks, it'll depend on what the kernel is doing. There are some CPU resources are shared between cores, like memory, for example. So the busier the machine is, the more kind of variation we're going to get in our benchmark results, which can be unfortunate. It might mean if we have a lot of variation, it might mean that we have to run kind of 10 times as many tests to find out what the real story is, to kind of statistically account for all of the variation. So I don't really want to deal with that. I want to run tests in a relatively pristine environment, so that I'm deciding, what variables to introduce. I do want to kind of stress the VM, but I want to do it in a disciplined way. I don't want to be impacted by over provisioned VPS providers or anything like that. I just don't want to deal with it, or have tests where they're running on multiple machines that don't have the same CPU model, that kind of thing. I mean, you can account for all of those things, but you have to decide if you want to or not, and I don't. So we're going to use RaptorJIT is going to use Travis for the functional tests, but we're going to use the same CI that we use for Snab for doing our performance tests, and that is the software is called Hydra, and it's an instance that's operated by Doman Kazar, who's a very, very good Nix hacker who came through Snabland and just kind of did a fantastic job of automating our infrastructure so that we can run our tests and our benchmarks in the way that we want to. So this is Hydra here. For our purposes, so Hydra has a bunch of build slaves. It's similar to Jenkins in some sense, but it's very Nix oriented. And our one has a bunch of machines available for running tests on. And some of these ones, like the Lugano servers, this is very specific hardware that we need for Snab. It has things like 100 gigabit network cards and that kind of thing. So that's really nice for running tests that have special hardware requirements. We can have the test declare its requirements and go and run on specifically machines that have the hardware that it needs. But we also have these 10 Muren servers, and these are generic Hetzner machines. So they all have an identical Intel i7 CPU, and Hydra has been specifically set up to only ever run one test at a time on each server. So what it means is I can define some benchmarks, I can have them farmed out across these 10 servers, and each benchmark will be running on an identical CPU with nothing else happening on the machine at the time. So the idea then is that when we decide that we want to introduce some variables into the testing, like we want to test more software versions, or we want to, well, anything that we want to do, then we can see the impact of that in our test reports, but we shouldn't see anything that's kind of irrelevant in the background, which is great. So all that we really need to do now is take the test suite that produced this report. So basically what we want is the CI to give us this picture, but automatically. So at any given time we can always go to the CI and see this picture to know how the next development branch compares with the master branch. And then if we were considering making a release, we would say, well, we can't make a release, it's blocked by this regression on the life benchmark that we need to at least understand before we can do that. So we have our Nix code over here somewhere. So when I ran the benchmark, let's see how I ran that. This is what I ran on the command line to ask Nix to run all the benchmarks, and it parallelized them locally on this machine because this is a 12-core server. So I already got some degree of parallelism just locally on the command line. So I said Nix build, make 10 parallel builds using the code in our test suite benchmark folder. The version A will be the RaptorJIT code in the current directory. Its name will be latest. Version B will be, its name will be older, and its source will be this other folder, and do 100 runs. So now I just need to replicate that in the CI. So there's two ways to set up jobs in the CI. There is the old-fashioned clickety way, and there's the newfangled declarative way. And I'm going to do it the old-fashioned clickety way this time. Oops, and I'm going to do it in Chrome because that's where I have my credentials. How can browsers choose so much resources? I have to be really careful actually what I do with the browsers so they don't kill the video streaming. So I'm sorry if it stutters while my machine is swapping. I'm streaming from Mac Mini, and I made the incredibly stupid mistake of getting one with a hard disk instead of an SSD, so it doesn't take much to throw it off its game. Anyway, let's hope it does okay here. So we're going to go back to our CI and log in there and set up a job to just automatically run the test suite. So signing in, and I already had a project called RaptorJIT. I don't really remember what I have here. I've run some. Okay, so I've run some other jobs in the past. But I think that I used the newfangled declarative feature to set this up, but I never really followed through. So I'm actually going to replace this. I wonder if I can just rename this. Let's see. I'm going to call this RaptorJIT declarative. Wait, hold on. Let me double check the state. I want to create a new. I don't have an option to clone that. Okay. So I have some older jobs I'm going to use for reference, but I'm going to create a new job set. Pardon me, I'm not doing this every day. I want to create a project called RaptorJIT CI. Which we can later replace the old one. And it will not be declarative. So we're going to create a job set manually, which I'm allowed to do because this is a non-declarative project. It's going to be called benchmark next. It's going to benchmark the next branch. And you're going to give it some inputs. So look at how the other jobs are defined here. So we can look. Let's look at the next code. Okay, so this is the next code that is going to run. These are the inputs that it wants to come in. So we just have to fill these in on the web form. Where did Chrome go? Okay. So I'm going to try to get both on the screen at once. We're going to have an input called a source, the source code for version A. That is going to be a git checkout. This is going to be the master branch. So we're going to get a git checkout from https github.com RaptorJIT master. Double check that that's the correct syntax. Yes. And we're going to say that a version name is a string which is master. Then we're going to have a B version source, which will be git checkout, which will be the next branch. And we will have a B version name, which will be a string, which will be next. The default is to do 30 runs, but we're still testing, so we'll do 3 runs. the hardware. Yeah, so we'll request Mirren hardware. Let me just check that's really implemented in the script. It's not. Okay, that's there for later apparently. So we'll need to check to make sure the CI actually runs this on the hardware that we want. I'm just going to leave this to default for now and see what happens. But we should actually specifically tell it what kind of server we want to run on, and then we could actually have multiple jobs to do some runs on Skylake and some runs on Haswell, for example, because the idea with RaptorJIT is that we want to aggressively optimize for the latest two major Intel microarchitectures. That's kind of the current focus anyway. In the future, it would be interesting to deal with AMD and that kind of stuff. But at the moment, the suite, the kind of the big wins are the Haswell and Skylake, and I would like to test each of them separately. One thing at a time. So, and the thing that we missed up here is to tell it what we actually wanted to build. And what we want it to build is benchmark results. No, I think we give it a source file. Let's say we want it to build test suite / bench. What's the name of this directory? Test suite / bench. And since we're actually checking out two versions of RaptorJIT here, we're checking out the master version and the next version. We need to pick which one we're going to pull the benchmarks from, and I think we'll take it from the next, so that if we update the benchmarks in some way on the next branch, then it'll do the comparison using the updated benchmarks. That sounds nice. We will have this every 10 minutes check for updates on the Git repository, so that it's automatically in builds, and we'll leave everything else at the defaults. Let's see what happens. We say, please create that job set. I'm getting no response. Why is that? This is some important field. No scheduling share. Okay, let's give it some. And now it's happy. Okay, so we have created a job set. It has never been checked. It's talking about the Git repositories. It has never been evaluated. Evaluated is when it downloads the Nix code and evaluates that to see what it's supposed to do. And the evaluation has been pending since 0 seconds, it says there, since 20 seconds. So what this means is that Hydra, which is the CI, is now pending the evaluation. So it's going to go off to GitHub. It's going to download those two Git repositories. It's going to run the Nix code to see what it's supposed to do, and then it's going to run all the benchmarks, we hope, or it'll give us an error and say that I screwed up one of the parameters. And one thing I want to check, what it thinks about that, I want to check in the Nix code to see whether we've done I want to see whether we've done the little bit of magic that you do to tell the CI what interesting files it should serve up on the web server, because it would be really neat to be able to go to the CI and just click around in the browser and see the benchmark reports. So I'll check if that's already done or if there's something that we need to do now. So where does it put it? Creates, yeah, okay, so it runs the benchmarks. It copies the CSV file into the output directory. It populates this magical file called Hydra build products to say that this CSV file is interesting, and then it also runs the R code to generate the two images, and it also tells the CI that those are interesting files. So the expectation then is that when the CI is finished building, it's going to say, hey, I've got this CSV file and these 2 PNG files that you might want to look at as a result of this build, which is nice. So how's that going now? Evaluation is still pending. Okay, so this, I guess this is something that's asynchronous. The next step is it will do the evaluation and figure out what needs to be built, then it needs to actually run the benchmarks. So that is something that we can maybe leave in the background and come back to. And meanwhile, we can be working on the thing that was next on our list. So this is partly done. Automate the benchmark interpretation. This this is an interesting one. So now we have this fancy benchmark report, and this is a blessing and a curse, right? Because there's a lot of information here, which is great if you have a problem that you're trying to track down, or you have time to check things. But it's also, I mean, it's a lot of information. It takes some time to read this, and it takes time and skill, because it's easy to fool yourself and misread, fancy graphs. So I don't want to have to read this every single time a commit gets pushed to GitHub. Actually, I want to only look at this when there is a problem, to understand what the problem is, or if I'm personally inclined, if I feel like, well, it's a long time since I read a benchmark report, I better take a look. So in some sense, I'm creating a maintenance problem for myself. If the CI produces one of these reports for every different software version, then those reports have to be used somehow. There's no use if they just go into dev null. But I don't want to read manually and think about the report every single time. That's just a lot of work. Okay, so it's fine when you're doing it before making a release once a month or something, but that's pretty late in the game to be finding out about performance problems. So it would be a really cool thing. I mean, you could do it that way, but it would also be a really, really cool thing to have the computer read these reports for us and tell us whether there's anything that warrants our attention. This is not a completely trivial problem, because there's a lot of benchmarks. They are not all, some of them are very noisy, like take this one here. The results are quite scattered. So it's a statistical problem to say whether there is an interesting difference between these benchmarks. It's not always black and white, So in some simple cases, this one doesn't seem to have a difference. This one does seem to have a difference that is very small, and this one does seem to have a big difference and also be shaky and everything. So what I want to do is have the computer somehow tell me, is there any interesting difference here? I want it to be able to distinguish between the case when there's no difference that can't reasonably be accounted for by random jitter, from the case where there is some difference that actually looks suspicious, that it looks like there is an actual meaningful performance difference on at least one benchmark between 2 or more software versions. So we need to apply a little bit of statistics, and I've already done something similar for Snap. So I already have an approach in my mind that's a bit swapped out, so I'll need to swap it back in. But this is to use a technique called the Kolmogorov-Smirnov test, which is a way to take two different distributions of numbers, in our case benchmark results, and test the hypothesis: do these can we reject the idea that these two samples come from the same distribution? So in other words, we want to test two software versions, and we want to be able to say, hey, these two sets of benchmarks results, we got A and B. Is it reasonable to think that they both came from the same software, or the software that has the same performance? Or is it more complicated than that? Or is it the case that there is some difference between them? For example, that one of them is faster and the other one is slower, or that one of them is faster on some benchmarks and slower on some benchmarks. Is there any significant difference of any kind that we can observe between these two benchmarks? And that's a pretty neat thing. So I need to swap it back into my own mind, so I'll talk aloud a little bit about how this test works. And to do that, we can first flip over to this other graph that's already being produced that we haven't looked at yet. So what we're seeing here is a so-called jitter plot, where we just, for each test result, we just plot it as a circle, and we introduce some random jitter horizontally to spread them out so that they're kind of, you can see visually, and the vertical position says the relative performance. The lower ones were slower and the higher ones were faster. Another way to look at the data is like this. This is with an empirical cumulative distribution function. So again, every graph has tremendous potential to mislead, and for every kind of graph, you kind of need to learn how to read it, and then there's also a lot of different ways that you can render it. So it always pays to have a sip of your coffee and think very carefully about what it is in front of you. And in this case, I only really want to use it as an introduction to the direction we're going with our statistical test. So let's look at this graph here to start with, just a different way of looking at benchmark results. So what this bottom left one is saying is on the x-axis we have a performance level compared with the baseline. So this point here is 120% performance compared with the baseline. This is 80% performance compared with the baseline. This we can infer is 100% of the baseline performance. And then on the y-axis, the vertical axis, it's telling us what percentage of the test results were below that level. So if we want to know what percentage of test results were 80% or less of the baseline performance, then we would come to 80% on the x-axis, and the y-axis we would go up and we'd get a reading of 0, which then tells us that none of the test results were 80% or slower compared with the baseline. So there were no suspicious slow results there, and it's got this big step, right? So it basically this is a really simple case where none of the results were particularly slower than the average. Pretty much all of them suddenly had pretty much exactly the average performance, and then basically none of them had higher performance either. So this is, and also we only see blue here, but there's actually a blue line and a red line that just happen to be on top of them. So this is what you expect to see for a benchmark that has very, very consistent performance, that always gives the same results, and none of the results deviate from the average particularly. And also when the two software versions being tested have the same performance. So we get this jagged step pattern from the consistency, and the fact that we only see the blue line and the red line is completely obscured tells us that the two branches were the same. So if we hop over to the other graph and scroll down and zoom in to a similar level, that's what we're seeing here, right? So on this one, basically every result for both software versions was exactly bang on 100% of the performance of the baseline. So then if we would look at a different one, like take the life benchmark that we were looking at earlier. In this case, there's two interesting differences. One is that there's a bit of jitter for both software versions, particularly on the latest one. So it's not always giving the same result. It's always giving the result plus or minus about 10%. And then on the older branch, it's always giving a different result, and plus or minus maybe 5%. So we expect this graph over here, when we come to the life, to reflect that and look different. So if we scroll up, so here is the life. So it's actually a little bit hard to read, of course, because I don't have the axis very well labeled when it's zoomed in like this. But what we see, let's find the 100% point. 100% is like, okay, it's the middle of the graph. So around about here is the, again, thinking about how we read these ones. If we want to know, sorry, that's the wrong one. I should be on the life. If we want to know for each branch, how many of the results were at least as fast as the average of the baseline branch, which was the red one. Then what we want to do is we want to come across here and get to 100% performance, which was in the middle. This x-axis point in the middle represents the test results that were equal in performance, or well, equal or below the performance of the average for the baseline. And then we want to come up the y-axis until that well, intercepts the red line in this case. And if we look across, now you can kind of see that I've made things hard here for us, because this is actually rendered on log scale on the y-axis. So the bottom half of the graph is zoomed in on the slowest results. So the idea of that is that if you have some outliers, that these will be emphasized. So maybe we're benefiting from this on some of the other graphs, but it's actually not very helpful here. If you want to know, if you want to kind of be able to read off values more easily on the y-axis. But anyway, just taking the short the short version, this point vertical line in the middle of the graph represents the test results that were at least half the performance. Sorry, were at least the same performance as the average for the baseline version, the red one. If we see where that intercepts the red line, we see that we're going to assume this is about 50% of the tests were at or below the average. And you can kind of see that it's not this really sharp jagged step. The really sharp step is indicative of a very consistent set of results, whereas this kind of smooth step is indicative of a bit more spread out results. So we said, hopping here briefly again, we said that the results for the red branch were a little bit kind of spread out around about 10% plus or minus, and that's being reflected here in the kind of the gradient of this line, and that it's not just bang step. And then if we look at the other branch, we can do the same exercise. So we take the middle point on the x-axis, which represents 100% performance, and we see where that intercepts the blue line, and that's actually down here at 0. So what that is telling us is that none of the results for the blue software version were as slow, were the same or slower than the average result for the red one. So that's also kind of makes sense when we come over here. So it's telling us that if we take this 100% line where the performance would be the same as the baseline average, that none of these results were down at that level. So that's a huge digression I've made now. I apologize for that. But it kind of becomes relevant because when we want to apply statistics, this is the mental model. So we're gonna use this this famous Kolmogorov-Smirnov test to automate looking at a graph like this and say, is it reasonable to think that the difference is due to random chance, or is that not reasonable? Does it seem to be based on some real significant difference between the software versions? And so I would hope that when we apply this test to the life benchmark result here, it will say no, there's no way in hell that came from a random difference, because this blue branch was in every single instance faster than the red branch. And I would hope that when I come over to this one over here, where there's a little tiny bit of difference, they're not quite perfectly overlapping, it would say, but that's that's kind of to be expected. It's very likely that those actually have the same performance. There's just a very, very small amount of random variation, and that's probably the reason that they were not exactly lined up. And then there will be more interesting cases like these. So I don't know what it should say about this. I actually hope the test will tell me whether this looks like a significant difference or not. And there's some other, so the neat thing about this test is that it's not just saying is the average performance faster, is the average performance slower. It's saying is the distribution of results exactly the same. So if there are any more outliers at the bottom, if there are any more outlying high performers at the top, if there is any difference in in kind of the step pattern, whether it's a bit, like whether it's this kind of smoothed out, longer, less consistent picture, or whether it's one of these really super rigid, consistent stepwise pictures, if there's any difference in those patterns from one branch to the other, then the test is going to fire. It's going to say, hey, there's something here. It's going to say, hey, something here you need to look at. So if we manage to automate this test, the expectation is that if the test says everything is fine, then what it's going to mean is that the data all lined up really neatly like this, and that there's nothing interesting to see, and that if we open the report, we're not going to find anything worth looking at. Whereas if the test says, aha, something's going on, then we're going to see a little red light on our continuous integration, and we're going to come in manually and open the report, and we're going to expect to find at least one interesting thing that is very likely not due to random chance, but is actually due to some difference in the software versions. So that's the goal. Now let's look at how that test is implemented. We can do this over on Wikipedia. Shall we go to begin with? Kolmogorov, this one. So I'm, to digress once again, I'm not a statistician at all. I like examining and diagnosing complex systems, and I've found that a certain amount of statistics is very practical. It lets you actually find answers instead of just running around in circles. So I spend a bit of time kind of looking for practical tools to pull out of the statistics world to apply to things like software benchmarking, but I'm not a statistician, and this really means you need to approach the problem with a certain level, with a large amount of humility, because it's the easiest thing in the world to kind of be the sorcerer's apprentice and go looking in the statistician's toolbox and pull out something completely inappropriate and completely confuse yourself. So I try to be very vigilant about this, but it's entirely possible that someone watching this has more statistical training than I do, and thinks that I'm on the wrong track. But anyway, I'll tell you. I'll put my head on the block and tell you the way that I'm thinking about this. So, well, first of all, there's two huge pitfalls. I'm digressing again. I do that. Two huge pitfalls that I'm aware of that I don't want to fall into. One is that when we look at our graph again, we got a lot of, there's a lot of it, right? There's a lot of these different panels. And the more panels you look at, the more chance there is of finding something spurious. So if we would come up with a test and then test this panel 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 and so on, there's a huge risk that we just will by randomness find something that seems significant, and this is just the nature of the game. This is the XKCD can explain this very briefly. So, scientists are testing whether jelly beans cause acne. They find no link. Statistically speaking, there was no link between having acne and eating jelly beans. So the appropriate thing to do then is to say, okay, well, too bad. We at least didn't have a powerful enough study to test that hypothesis. But the trap you can fall into is to then test every color of jelly beans separately. And then somewhere in the middle there, one of them kind of randomly happens to look like it has an effect, just because there is a lot of randomness and you're doing a lot of tests, and if you test for long enough, you're going to find something randomly that looks significant. So that is exactly the trap that we potentially fall into here. If we test each one of these, it's entirely possible that this one, for example, or this one will have a difference caused by some background random behavior that that seems, that crosses the threshold of significance. So I want to specifically defend against that. I want to specifically defend against that. And there's two main ways you can do that. One is to make a correction. So to say, well, I'm testing multiple hypotheses. I need to adjust my my thresholds to take that into account. That's one way to do it. But I have a simpler way that I want to do, which is actually to just take all of these results and just chuck them into one great big combined distribution. So we're going to get one crazy jagged line that represents every benchmark result, and we're just going to do one test on that, which I think is valid. The cool thing about this, which kind of brings us directly to the second pitfall that we need to be aware of. So there are kind of two kinds of statistical tests broadly. There are parametric tests and there are non-parametric tests. A parametric test is one where you make certain assumptions about the distribution of results. So for example, if we would assume that all of our benchmark results kind of fall on a bell curve, so there's a point in the middle, the average, which most of them are close to, and then they kind of, to some extent, they kind of deviate evenly, smoothly away from that average point. If we would make that assumption, then we could use a whole bunch of these clever shortcuts that statisticians have come up with over the years, and that particularly were very important before we had computers for being able to actually get calculations done. But we absolutely can't do that. Sorry, wrong window. With our data. So if we pull up our data again, so just looking at what we have here, it's a little bit kind of all over the shop, right? We have this benchmark has a bimodal distribution of results where there's two different clusters. This one may be on a bell curve. This one is obviously has a lot of outliers on the high side, not so many on the low side. So basically, it would not be good to just kind of pick these, to talk about means and standard deviations and that kind of stuff. We would be running a major risk of coming to the wrong conclusions and missing a lot of information because this is just data that doesn't follow any particularly known distribution, and that's going to be doubly true when we do what I just said and take like each of these data sets. So this panel here has 100 red and 100 blue results. This one here has 100 red and 100 blue. And what I propose to do is take all of those data sets and just squish them all into one. So we're going to get a big scatter plot that just has blue and red kind of all over the place for all the benchmarks. It'll be cool. We will actually do this. And then the question we're going to ask, the thing that we're going to automate is there any difference, do we think, between those two crazy distributions? So that should be quite cool. We'll see how that goes. And again, I've already done that once for Snap. I don't have it swapped in at the moment, but I'm hopeful we can just whip that up. And now with those digressions out of the way, I'll show you back to that Wikipedia page. We'll see the test that we're going to use and why it kind of is reasonable. So we're going to use something called the two-sample Kolmogorov-Smirnov test. Which we see here. So we're gonna benchmark two, well, or more, but let's say two versions of the software, the master branch and the next branch. And suppose that the master branch is in red and the next branch is in blue. Then we're going to come up with some line like this that is going to represent every result of every benchmark. So it's gonna have a bit of a funny shape because we're mixing a lot of different benchmarks in together. And on our x-axis we'll have something like the number of cycles that it took for the benchmark to complete, or how long the benchmark took to complete. And for some benchmarks it will naturally be a short time, and for some it will naturally be a long time. For some it will semi-naturally be a lot of variation. if they manage to provoke the JIT in interesting ways. So we're going to get an interesting kind of a line, and then what we're going to want to do is have the CI software tell us, is there a difference, a real difference, a meaningful difference between the two lines? And the way that that works with this test is what you see visualized here on the Wikipedia page. So it's essentially what it's going to do is to produce these two graphs and look for what is the biggest distance between the two graphs at any point. So this distance here is what we're interested in. So for, I mean, if there is any point in the graph where there is a really big distance between the two lines, then that is indicative of a significant difference between the results. And if they track each other very closely, then that indicates that they may well have the same performance. And the actual, how much distance is okay is a kind of a magical table lookup. It depends on how many samples we have. So if we have 20 benchmarks and we run them 100 times each for each software version, then we're going to have 2,000 samples for the master branch and 2,000 samples for the next branch, and we're going to be able to do essentially a table lookup for this Kolmogorov-Smirnov test that tells us how much distance between the two lines is reasonable based on that sample size and how much is suspicious. So putting that once again back into the context of our the benchmark results we had before, I mean, we have some of these graphs. So the test, I mean, again, we're going to actually test an aggregate of all of this, but in principle, we could apply it to each of these individual tests. So like on the life benchmark, it's going to say there is this massive gap. It's the whole, this at this point, the red line is at the very top and the blue line is at the very bottom. That's the biggest difference you can possibly get. So absolutely, the test is going to say that these were not the same. Whereas for this one, I would imagine this one's also going to fire as well. But anyway, in every case, there'll be a threshold. It's going to be looking at the maximum distance and saying, is that plausible due to randomness or not, which is cool. So the next step on that one is actually going to be to fire up R, which I haven't fired up in a long time. I probably embarrassed myself with forgetting really basic things, but that's live coding, I guess. But before we do that, let's have a look, and maybe we'll also take a short break to fill up a coffee cup before we do that. But right now, let's just hop back over to the continuous integration job. Whoops, that's me editing my page. Hop back over to the continuous integration job we set up to see if that's working yet, just so that in the background we have that running, because it'll be neat to see that run later. So was there an error or did it run? It's still pending. Okay, I don't know why it's pending for so long, but we'll let that keep doing its thing in the background. So back in 5 minutes to take a look at firing up RStudio, doing a little bit of R hacking, and automating our interpretation of test results. See you soon. So here we go again. Drew Hess kindly tweeted me just now to say that I forgot to click one of the enable tabs in the CI when I set up my Hydra job. So I fixed that now in the break. Hopefully that will we can check on that later to see if it's running now. But now is the time to fire up. Take a deep breath and fire up RStudio and do some R hacking, which I haven't done in a little while. So hopefully I remember some things and digressing once again as I'm wont to. R is a really, R is basically a Lisp dialect. It's a pretty cool language. One of the notable things about R is it's used by a lot of statisticians. They've implemented a lot of stuff in libraries. Very, very often when you want to solve a problem in R, there is a library that solves it for you, and it's a question of finding that library and using it. And this really exposes you to dependency hell, because you have a huge repository of packages out on the internet, thousands of packages being updated furiously, and they all depend on each other. And what I've found in the past is that when I write some R code on my Mac, I have a very little chance of actually successfully deploying it on a server with Linux later, just because I don't have the same package versions of everything. When I've been hacking away on my Mac, I just ask for the latest version of everything, and then when I go to deploy, it doesn't work, and it's miserable to debug. So I'm actually going to start using R in a different way, which is via Nix. So I'm going to have Nix install the RStudio IDE on a Linux server, and then I'm going to run that. I'm going to access that from my Mac, and then when I go to deploy this to the CI, I'm going to deploy that with Nix as well, and it's going to use exactly the same version of every package is the idea, and hopefully every package that we need will be already bundled with Nix. Let us see. That's the plan. And I guess we'll see how that goes. I haven't tried remotely running RStudio lately, so if there's any hassle there, we'll just fire it up on the Mac and port it later. It's not the end of the world. We will try it briefly too. So I'm going to want to reconnect the server with X authorization. I hope I have an X server installed on my Mac. X forwarding setup failed, untrusted, XAuth key data not generated. Okay, I'm not in the mood to fight with X, but it would be a nice way to do it next time. I'm just going to start RStudio on my Mac and be aware that there is some potential for a need to port this later if I start using some R libraries. I guess the other thing is that RStudio, so I hope it works on this screen size that I have here. I'm doing this streaming from a corner of my screen. I'm only using a quarter of my screen, so normally I have luxurious large windows. Now I have little YouTube-friendly windows. I hope there's enough space to do some R hacking. I'm sure there is. Sorry, that was just me on the camera all the time. Apologies for that. Here is RStudio. Digressing again, RStudio is actually kind of one of the inspirations for this Studio open source project that I'm also working on. I enjoyed working in RStudio because it just automates a lot of basic stuff. And I thought, well, it would be nice to have a Snab studio. And I thought, well, it would also be nice to have a RaptorJIT studio. And then I thought to myself, it's kind of a pity if you need to build a new kind of studio again from scratch every single time for every project. So wouldn't it be nice to just have a general studio that you can integrate all of your development tools into, and also that doesn't make you use some kind of crappy half-baked text editor if you already have another one that you like. And so that's what Studio is. So here we go. We will start a new file. We're going to need some data to work on, and I think we'll just take the CSV data from the benchmark that we already ran. So I'll just copy that across from the server, as I already copied the PNGs. I find the right shell. So on the server, we have a folder called result, which has a file called bench.csv, which contains 5,200 samples, which sounds about right. So let us copy that across. And we'll, as a first step, we will load that into RStudio. We will say there's a lot of different ways to read CSV data in R, and let's check which one that is. I will say I'll load a library called the tidyverse, which is this Hadley character. So Hadley is like the superstar R hacker. He does amazing libraries and often replaces standard libraries with other things of his own invention. Reading CSVs is one of those. So is it read.csv or read_csv? Read R. I'm going to use read_csv. Of course, I should use read_csv, not read.csv, which is what I had there already. Okay, so we will read the CSV file and assign the result to a variable called bench. Okay, so this is just a little rendering of our CSV data that we got from the benchmarks. So these are our columns. We have a letter A, B, C, D, E for each software version that's being tested. We have a version which is a string name. So the version A is called latest. We have the name of a benchmark. We have the run. This was the first run of that benchmark. We have the number of instructions that executed as reported by perf. We have the number of cycles that it took, also as reported by perf. So the graph that we saw before, I'll just pull that up briefly, is just generated based on this data. So the Nix code here has this script called generate.r. Which in turn loads a file called bench.r. And this is the code that generates those graphs. It's from a library called ggplot, also written by the illustrious Hadley. So we're going to just write something kind of similar to that now to do this new thing that we want to do. So what I would like to do actually first, to do the statistical test to see if two branches have the same performance, it doesn't require any visualization particularly, but to keep our feet on the ground, I'm gonna start by visualizing things. So now I have to swap back in the syntax to ggplot. There's another thing with this ggplot library is everything you want to do is already there. It's just a question of what parameters to give to things, and it's generally a lot of kind of Googling and reference consulting and so on. We'll see if I can do any of it from memory. So we're going to plot the bench data. What we're going to do now is this this combined CDF of all the benchmark results for one branch versus the other. So we're going to have an aesthetic in which the x-axis is the benchmark result. No, sorry, it's cycles. The x-axis is going to represent the number of cycles that elapsed while the benchmark was running. And we're going to view a spherical cumulative distribution function based on that. And that, cycles. Okay, so actually that is the graph for all of the benchmark results without splitting them out for each version, which I forgot to do. So again, we have the, why do I keep pulling up these images from my channel editing? We have these graphs before, so this is split out both separately for each benchmark, one graph for array3D, one for binary trees, and also by software version, a blue version and a red version. And what we have over in R is just everything combined into one place. So that's what we see here. So we see that some of the benchmarks took a really long time. Some of them took a really short time, and it was a big kind of a spread. The next step that we want to see is we want to split this out and see it separately for each software version. So we do that by changing our aesthetic to say that we want to choose a color according to the version, which is a bit better. So this, zoom out. So actually this is the overall result that we want to make a statistical test on. This is what we're going to, so we're going to test the hypothesis that these two CDF graphs came from software with the same performance. And the test is going to tell us that, okay, yes, it's pretty believable that they had the same performance, or it's going to tell us that no, it's highly implausible. And we've already seen, this is what I think is the awesome thing about these non-parametric statistical tests, that this is messy data, right? It's following a crazy pattern, and the test is just going to tell us, is it the same? And it doesn't make any assumptions. There's no bell curves here. There's no means. There's no standard deviations. There's just how far are these lines allowed to deviate from each other before, statistically speaking, it's unlikely that they come from the same software. Really cool. So let us actually just run the test, perhaps. I think there's a function called ks.test, if I'm not mistaken. It'll probably take a couple of goes to find the right syntax for this. ks.test is a library that implements the Kolmogorov-Smirnov test. Okay, so it wants us to give us two vectors. So I guess that we're going to need to filter things out. So the first, so we have everything in a table, like from the CSV at the moment, but this is going to expect us to just get two sets of numbers. So we will need to do some in principle, trivial R hacking to do that. So if we filter the benchmark data to get just the ones in which the version is A, and then from those we pull out the cycles column. Let's just do that on that by itself to see. No, that didn't match anything. Not the version was A. The letter was A. That looks fine. Okay. So we're going to say, we'll just put this in a variable. We'll say that the A version is that. Whereas the B version is that. And then we'll do our KS test to compare the A version with the B version. And this is actually kind of neat as well. There are three different ways that we can do the test. We can do a two-sided test to just see if there is a difference between the two data sets, or we can do a less or a greater test, which is actually asking specifically whether one of them at any point has beaten or been beaten by the other branch. So this is actually pretty neat, that we can decide whether we want to have it flagged when there's any significant difference, or only if we want to see improvements, or only if we want to see regressions. We'll just keep it simple and do the two-sided test for differences now. So it's not very dramatic, right? That was a huge amount of build-up. I was talking for probably 2 hours about all of this stuff, and actually that's kind of what it comes down to. This, hang on, there's probably a better way, to format that. Let me check. But no. Okay, and just take it raw. So we run the KS test comparing the A and the B. It does a two-sided test, and this D is the distance that it found between the two plots. But we can look at the p-value. P-values have a very bad reputation these days, but we're going to look at this one because of the factors we thought about earlier. The p-value gives us the likelihood that oh god, you have to be careful when you explain p-values, don't you? P-value is telling us more or less the likelihood that we would see this much of a difference between the two graphs if the performance is the same, and the likelihood, you know, is 1 for absolutely and 0 for never, and what we have got is a very, very, very small number. So what it's basically saying is that there's no way in hell that these two branches have the same performance. So this this test is coming up. It's coming up and saying that what would you say? If we were doing this on the CI, this would be a failure, in the sense that the new next version of the software doesn't have the same version as the old version of the software. So the only thing that remains to be done is, I mean, it's not okay. Digressing slightly more again, this is actually giving us basically what we need. For now, what we want to do is hook this into the CI and just get a flag, yes or no, do these branches have the same performance? And maybe we will restrict that to saying, is the new branch slower than the old branch? Probably we do want to do that. But another cool thing that we can do, which we will probably do later, but I'll just show you on a screenshot, is to put confidence bands around the graph so that you can interpret them visually a bit more easily, which is based on the same statistic. I'll just show you how that looks. I've got somewhere on my RPubs. Yeah, so this is how it looks in the report that gets generated for Snab. The latest development version anyway. So then you get it's the same graph, although it's very smooth here because on Snab we do like many thousands of tests, and you get a confidence band around them. So if you've got blank space between the confidence bands, that's probably indicating that there is a real difference. Whereas here, where there's a lot of overlap, probably is not a difference. So it's a visual way to kind of do a very similar thing where you just plot the two lines and you give them confidence bands. So if the confidence bands are overlapping everywhere, then yeah, there's a fair chance that they're both the same. But if there's gaps between the confidence bands, then it's very unlikely that they do have the same performance. So anyway, eye on the ball. Let us go back and take this surprisingly short, actually, R program that we came up with, and let us implement that in the repository so that we can run it from CI. So we'll write some Nix code that executes that test right now. So we already have some Nix code here for our benchmark. We're going to add something new, which is a benchmark regression. No regression. So it's we have to revise this, but at the moment this is just going to fail to build. Is that too rude? Yeah, why not? For now, we'll have it. Actually, we'll make the build fail if there is any regression in the benchmark. Fix that later because we don't really want the build to fail. It can have other unintended consequences. But we're going to have a name of this will be benchmark regression. Oh, before I go in that, we need the way that we're going to implement this is we're going to pull out the p-value from this KS test. Yeah, like that. So we're going to say if we want to be with 99% confidence, for example, we will test whether the p-value is less than 0.01. And in this case, it would say true. Whether we, that we have a 99% confidence that this was the performance of these two branches is different. So we'll do it like that in the R code. Benchmark, no regression, build inputs. We're going to use the benchmark results because we need the CSV from that. So the build inputs will be the benchmark results, and we also need R, right? And we might need a special package for that KS test. We'll need to test that. What package is the KS test in? A package called stats. Maybe that's there by default. I don't know. Let's guess. We'll get an error if we try to call it and it's not there. So, and then we will write this is going to be modeled on the bench.r script. We run that. We ran that. Okay, generate.r. You know what? For now, we're just going to be lazy. We're just going to piggyback this on the R code that already exists. So we already have a file called generate.r. This does already run some code to generate the benchmark on those. So for now, I think we will just put this in here as well. We'll generate a little flag saying whether it was okay. It will store the p-value. So here we already have the data here, and we're going to just reproduce basically what we did before. We'll say run a KS test on filtering the data such that the letter is the A version. We're going to do a test for 2. Filtering the data where the letter is the B version. In both cases, we want to grab the number of CPU cycles for the benchmark to look at. And we will run a two-sided test just to see if there's any difference, positive or negative. We're going to want to write, so in principle we want to write to a file, but let's be lazy and print it as a message. We're going to say message KS test p-value is this could be something. And this is interesting in a different way. So I'm hacking the Nix code. So when I ask Nix to run the benchmark, Nix does a lot of caching, and I have to be a little bit thoughtful. If I modify the Nix code in any way that impacts the way the tests are run, then the tests will need to be rerun. But if I only modify things that use the test results, then it should be able to reuse all the test results, provided that they're still in the cache. So we'll put that to the test right now, and we will just build this. So I'm rerunning the benchmarks the same as I did before now, and I'm really hoping that it doesn't actually rerun any of them, because they should be the same as the last time I ran it. Although I probably screwed that up because I'm making changes directly here in the directory that I'm testing, which is a bit of a no-no. Okay, so I'll just do it with one run in that case. While that runs for a moment, let us pop back over. I need to think a little bit about how to get a good kind of edit, compile, run loop for hacking the benchmark reporting. I think I'm very close, but I just need to make sure that it always reuses previous benchmark results. But while that's there, we can pop over to our CI again and see whether that hot tip I got on Twitter has helped, and whether actually we're getting anything building there. Okay, we had errors. I'm trying to find the input containing the job expression. Did I screw it up somehow? I said in test suite / bench, but I think it's probably in RaptorJIT / test suite / bench. Or is it on the other job? Let's try that. See if that's better. It's interesting having to deal with all the different environments. Having the code on the Mac where I often do my R hacking, and then having the command line Nix environment, and then having also the Hydra web environment. So they're all kind of doing the same thing, but I need to find the input containing job expression. I said in input next, but of course I should have said in input B source. Sorry, let's just fight with this for a moment. I mean, I'm parallelizing a little bit now because I want to do two things. I want to get the CI generating the graphs, which will be really nice for looking at, and then separately, and that's what I'm looking at now. And separately, I'm trying to get the graphs interpreted automatically, which will be really handy. Deal with errors, so maybe roll back the other change that I made. Spell that out. This job set as well. I was not allowed in restricted mode. Okay, so this is something that's allowed in later versions of Nix. I have inside my Nix code, and I'm just kind of diving in and doing things. I'm sure the context is not completely clear watching this, but I guess that's live coding. In my Nix code, I actually specify which version of Nix packages, which basically implies the entire software ecosystem, the version of R, the version of RaptorJIT, the version of GCC, the version of glibc, the version of like everything that is used for executing the tests. I specify that in this file called packages.nix. But you're not allowed to do that in Hydra. Hydra wants to be responsible for fetching all of the inputs off the internet, so it's not happy. It's running in a restricted mode where I'm not allowed to go off on the internet and fetch new package definitions. I think that will actually be supported with newer versions of Nix, but I'm not sure. It would be nice because actually I want to be able to choose all my software dependencies in the Nix source code in the Git repository rather than on the Hydra UI. I would like Hydra to just do what it's told. But for now, I'll be nice and I will come in and I will give a new input where called packages. So instead of taking the default value, which is what goes off and fetches from the internet, I will put a tarball there. Really see. In that case, git checkout, and it will be that. Okay, so it's taking a specific commit of the Nix package definitions. So again, it's using exactly the pinned versions of everything of the entire software ecosystem, pretty much the whole distribution. But now it's being pinned in Hydra rather than in the Nix code on disk. Let's see if that worked any better. Evaluation is running now. Okay, let that run for a while. We'll come back to that. We'll context switch again to what we were looking at before, which is automating the interpretation of the test results. And okay, so I should really slow down for 1 second and think about the way they want to do that. So my first thought was that if there's any regression or difference in the test results, then this would be a build failure. But that's going to be really annoying in practice because it might prevent the graphs from getting generated and that kind of thing. So that's actually not what we want. So for now, what we might do is just write a file, a little text file that says success or failure. That's probably a reasonable way to go. So then when we're going to review CI results, we can just look in that file, and if it says, same or different, maybe we'll say. If it says same, we know that when if we do look at the graphs, we're not going to find anything interesting. And if it says different, well, we don't. It's maybe overstating it. But anyway, if it says different, then that's going to be a strong indication that it is worth reading the graphs. If it says same, it's going to be a strong indication that it's not worth reading the graphs, although you should always look at the data from multiple angles when it counts, like when you're making a release and that kind of thing. So this would be more just during development to speed things up. Okay, so we were already in the generate.r, and I was making it print a message, and we were running our benchmark. It said it has not got enough data. Which might just be because I ran the benchmark with only one run. If we run it with 2 runs, okay. But while we're doing this, I will step out of that directory because the reason that it's rerunning benchmarks now is that I'm generating my output into the source tree. So every time it looks at the source tree and does a hash on it, it thinks that it's changed just because I'm writing the result of the previous build in there. So I should just stop doing that. Which I will now. I remove the JIT. Well, no, it's worse than that, isn't it? Because the source tree includes my R code, so I'm actually a little bit screwed there from a workflow perspective. So I need to think a little bit actually about how I can. Well, I know how I can do it. I'll make a separate checkout, where we will edit the R code, and that will be separate from the ones where we actually have the code that we're running for the code under test. So if we just say git clone this RaptorJIT repository into RaptorJIT R, and we pop into RaptorJIT R, we need to get those in-progress changes that we had, okay, which was just this. It's so simple, we could just copy and paste it. We can actually just save that file in Emacs. We save that one in the new repository. And set that repository back to the pristine sources. So now we have 3 checkouts here actually. We have RaptorJIT, which is the master branch for being tested. We have RaptorJIT old, which is the older one for being tested. We're testing in benchmark. We have RaptorJIT R, where we're hacking the report and where we're going to make our changes and where we're going to not screw up this is the software under test. So now we want to do a build. We're going to run the benchmark code from this repository, the RaptorJIT R. The A source is not going to be this directory. It's rather going to be that one. And we'll give it, let's say, 3 runs this time, so that we don't have to spend a lot of time waiting for it. And while that does 3 runs of the benchmark, we'll pop back over to our browser and see if anything happened over there. It's still evaluating, which is probably a good sign. So I mean, Hydra is a little bit opaque when it's evaluating things, but in this case, it's some new job that I'm running. It's very likely that it needs to go off and download and possibly build a bunch of dependencies in order to chug on this. So I'm gonna take its delay as a good sign and imagine that it's off downloading a bunch of stuff that I need. Meanwhile, we can come back to our shell. Okay, so it's still running the benchmarks, but it's not going to take a terribly long time, so we can probably afford to wait for a moment. And maybe this is a good time to think again about recap what we're doing here, actually. So what's happening on the CI already is we're automating the process of creating these graphs, this graph and this graph. So every time we push new code to the next development branch, it's going to be automatically benchmarked, and the CI is going to produce a diagram like this that gives us an idea of how the next branch compares with the master branch. And we're going to use this to inform our development, see if we've messed something up in a change that has been merged for integration, and if so, then to fix that and get a clean bill of health before we push to the master branch and make a release. So that's kind of going to be what gates the RaptorJIT release process. We're going to run all the benchmarks we have available, and we're going to check for regressions on them. And then what we're trying to further do is to automate the process of checking if there are any regressions there. So we want the CI to not only give us the graph, we want it to also give us a flag telling us whether to bother reading the graph or not, because I suppose it takes 15 minutes to properly sanity check a graph maybe, and it can be ambiguous. Computers, I would rather leave things like checking confidence intervals to computers rather than gut feeling, because brains are just designed for leaping to wild and wrong conclusions. Computers are much better, or at least they're very valuable as an additional sanity check in that department. So this still was not accepted. Still saying I didn't have enough data, but I gave it 3, which I would have thought would be enough. So it's probably actually a bug. I probably have the wrong filter expression here or something like that instead. So how do we do that over here? What it could be is could be that we're using a different version of the filter function. So something I find really tricky with R is that it's got a bunch of built-in functions, and sometimes someone very clever has made a much better version of those functions, like this Hadley character, and that's great. And if you always have those new ones loaded, then life is good. But it can also get tricky if you have different functions with the same names, and the one that you actually get depends on which modules you've loaded and in what order. That's kind of just a pain. So it's possible that when I was calling filter there, I was not getting the filter function that I thought I was getting. I was getting another one. So I'm just going to check. Just going to check what's going on there. So this is also kind of interesting. So I need to think a little bit about this as well, because now it's rerunning the benchmarks, which I was thinking wasn't going to happen because I've separated out the R code, and I don't know why that is immediately. So I ran this build. The benchmarks are rerunning. I wanted the benchmarks to be reused. I wanted Nix to say nothing's changed in the benchmarking environment. I can reuse those results. I can reuse that CSV and to then just actually execute the last step in which the R code runs. But that's not what happened, obviously. So that's something I need to figure out. So in the short term, to get this more productive read eval print loop going, I might need to just reduce the benchmark size and then bite the bullet and figure out a proper way to do that. Meanwhile, this gives us the perfect opportunity to pop over and see that Hydra is still busy. 9 minutes going. Okay, again, I assume that it's off downloading all of my R dependencies and maybe building a Fortran compiler and whatever else needs to be done to make all of the R code happy. It can take a while when you do it the first time. Okay, there's no package called tidyverse, so we need to install that. I mean, we have two options here. We either install this dependency, probably straightforward and reasonable, or we just figure out what the base filter function, how that works, and if we can use that instead. So let's take a quick look at that. Let's search the R image for functions called filter. What do we have? We have a function called base filter, and we have a diplia filter. Okay, so I think that that's the one that I want to have, and this is the one that I'm actually getting. So let's see if the one that we're getting can be made to work. So this seems to be all variants of fold. It wants a function. Okay, let's just see if we can backport. Well, how do we want to do this? Do we want to pull in the dependency? I mean, we're going to need it sooner or later. The base R is very limited. It's very tempting to try and be a caveman and avoid dependencies, but actually with Nix we shouldn't have to, because when we pull in the dependency, Nix is going to pull in a very specific version of that dependency. It's not going to change until we ask it to change, until we ask it to upgrade to a new version of the Nix packages. When we do that, if we have any problem, we should see it immediately, because it'll impact our testing. We'll get a failure to build the benchmarks, and then we will be able to do a git bisect to see what dependency was an issue. So I think the right thing to do here actually is to install the extra dependency, even if we maybe don't strictly need it, because we're not supposed to be feeling bad about using dependencies when we're using Nix. Nix, this is the idea. We're supposed to get dependency heaven, where we're just happy to use all these dependencies. So let's see how close we can get to that. So diplia or dplyr, or however you say it, that's the package that we really want that has this filter function. We'll search the Nix package collection to see what that's called. Well, taking again the opportunity to check our other build. We've got an error there. What was it? Undefined variable standard env. Okay, so that's something I need to take a look at. I don't immediately know what the reason for that is. I'm sure it's something simple, but I don't know offhand. So I mean, I need to come back. Maybe we'll take it the next time around. Have a look at getting the graphs generated off the CI. But I want to get something working right now, damn it. So while that runs, we'll have a race. We'll see how long does it take to search the Nix packages versus how long it takes to write a version of this that doesn't have the dependency. So what's happening? This is what happens when we run the write filter function. If we run instead the base filter function, there's a couple there, wasn't it? What we want is a function. So okay, okay. I would like to use dplyr. Didn't find anything. Okay. I'm sure that at this point, any Nix gurus who are watching are turning in their chairs, thinking, "Why doesn't he just do, this simple thing to find the right package name?" In that case, it would be great to shoot me an email and tell me how I should be doing this. I'm just going to open the Nix packages definition and just go straight into the R modules source code, and I'm just going to grep for the package that I want. Okay, I think it's just got the obvious name. Okay, so we're going to put that. I'm going to add that dependency to our Nix expression. So when we run this script, we're defining the environment, what software is available. No, we already have it available there. Okay, I'm fooling myself. So that specific library is already available in the Nix environment, but I was asking for the tidyverse, which is a larger collection that includes that library and other things. So maybe if I just ask for that, it will work. And then since we were getting more tests rerun than what we wanted, we'll just go in at the same time and edit the definition of the tests to just run a few, because we don't want to spend all day waiting for the tests to run, when really what we want to do is just debug the R code. So let's see what happens this time, whether we get a result out at the end, whether it reruns the tests, and how many tests it runs. Hang on, how many? Oh, 3 runs, okay. 3 runs for each branch, okay, right. So we expect each benchmark to run 6 times, 3 times for each branch. Fair enough. Still didn't work. Is there a genuine bug? It's interesting with this live coding thing because, of course, a fair amount of a programmer's time is spent just staring at something that should be obvious and should just be working, but actually doesn't. So I hope you appreciate the authenticity of sharing that on a live stream. Heavens. Yes, test. Filter the data to get out the rows where the letter is A. Pull the cycles. Do the same for letter B. Okay, so data was from bench.read. Is this giving me what I think? Yeah, maybe. Okay, so actually, this may be my problem. So the bench.read is doing some fancy processing on the data in order to make it usable for generating those other results. The graphs that we had were all normalized for all of the results and not in CPU cycles, but are as a percentage of the average of the baseline, that kind of thing. So actually, maybe I'm confusing myself and using the wrong format for the input. So we'll just check for that, and we'll say instead we will say that the KS data is read CSV. I'm going to use read.csv because I'm not confident at the moment that read_CSV is available. Okay, I could arrange that, but anyway, here we go again. I need to think about how I'm going to do this with my R stuff. I kind of feel like the right thing would be to just wildly use every dependency that I fancy, just chuck them all in there, and then let Nix save me. But I guess I need to. It's really like climbing a rock wall. You need to learn through experience to really trust your safety harness. You always have the reflex to avoid dependencies if you don't think that you need them. So for now, I will use the built-in CSV reader in R and hope that that's just fine. And then we will use this raw KS data when we do our KS test. So let's run again. Same error again. It's quite tricky actually. I get very comfortable in the RStudio environment, but then I tend to need to run the code then in a in CI in an automated way. I want to have it checked in a Git repository and that kind of thing, and I tend to do that by just kind of often by just rewriting it. So in this case, I have the code working in one window. I'm trying to get it working in the other window, and it's a nuisance. Make absolutely sure that we're using the Dipley version filter. It doesn't help. Okay. So I kind of get the feeling that this is something that once I turn off the stream, the solution is going to be completely blindingly obvious to me. So I think maybe I'll stop struggling and take a break for lunch now, and maybe I'll open the stream again, or I'll do a little bit of background checking on the two things that we're stuck on here. One, which is why does this code that works fine in RStudio not work when we run it in the automated environment on Linux? And the other question is why does Hydra make this specific complaint when I try to run everything? So if we fix this, then we're going to get the graphs appearing on the CI, and if we fix the other thing, then we're also going to get a file telling us whether the graphs are worth reading. So this is kind of worth the effort. This is something that's probably going to pay for itself very quickly in terms of not shipping breakages, not introducing regressions, and it's something that we can use for years and years at a time. So certainly in Snabland, we have a similar performance tests, and it catches potential regressions in every release cycle, and we just would have a hard time not having it. We've been using that for a couple of years now, so it is worth some hours of effort to invest in setting up. Anyway, I'll switch off this now and pop back another time, maybe this afternoon or tomorrow. We'll see.